Imagine a bridge that withstands the weight of countless vehicles, or a skyscraper that rises above the city without swaying in the wind. These feats of engineering are possible thanks to our understanding of how forces act on objects. In this video, we will develop part of the theory of forces, starting by defining what a rigid body is. A rigid body is an idealized model of an object that does not change its shape or size when subjected to external forces. It's like a frozen snapshot of an object, which allows us to analyze its behavior under various load conditions. In the study of bodies, we differentiate between two types of forces, external and internal. External forces originate outside the rigid body and act upon it. They can cause changes in its motion or equilibrium, either through translation or rotation. Examples of external forces include gravity and friction. Internal forces, on the other hand, arise within the rigid body due to interactions between its particles. They do not directly affect the body's motion or equilibrium since they cancel each other out. An example of an internal force is cohesion, which holds the particles of a solid together. In this video, we will focus on analyzing external forces and their effects on rigid bodies. The transmissibility principle states that the effect of a force on a rigid body remains unchanged if we move the force along its line of action without altering its magnitude, direction, or sense. This means we can slide the force to a different point on the rigid body without changing its impact on motion or equilibrium. Forces acting on a rigid body should be represented by a different type of vector called the sliding vector. This allows forces to slide along their line of action. The consequence of the transmissibility principle is the concept of equivalent forces. Two forces are considered equivalent if they have the same magnitude, direction, and sense, but act at different points along the line of action. The transmissibility principle and the concept of equivalent forces are fundamental tools for analyzing force systems acting on rigid bodies. The vector product or cross product is a mathematical operation applied to two vectors in three-dimensional space. The result of the vector product is another vector perpendicular to the original two vectors. It is represented by the cross symbol and is calculated using the following formula. The magnitude of vector v equals the product of the magnitudes of the two original vectors multiplied by the sine of the angle between them. It's important to note that the vector product of vector A by vector B yields a vector with the same magnitude, equal direction, but opposite sense compared to the vector product of B by A. The vector product does not satisfy the commutative property, although it does satisfy the distributive property as shown on the screen. The vector product also does not satisfy the associative property. The vector product has various applications in physics and engineering, such as calculating moments of forces, which we'll explain in the next point. Another way to calculate the vector product of two vectors expressed in rectangular components is by using the following formula, where px, py, pz are the components of vector p in the x, y, z axes respectively. Qx, qy, qz are the components of vector q in the same axis. If we expand the terms to calculate the determinant of the matrix, we obtain the following expressions. This formula allows us to calculate the vector product without needing to know the magnitudes, directions, or angles between the vectors. The moment of a force with respect to a point measures the force's ability to rotate a rigid body around that point. It is defined as the vector product between the position vector from the point of force application to the reference point O and the force vector. The moment is represented by a vector perpendicular to both the force and position vectors. The formula for calculating the moment of a force with respect to a point is as shown on the screen, where r is the position vector between the point of force application and point O. F represents the applied force. The magnitude of the moment vector can be calculated using the following formula, where d is the minimum distance between point O and the line of action of the force. Theta is the angle between vectors r and f. The moment is measured in units of Newton-meter or pound-foot. The calculated moment is a vector perpendicular to both r and f. The sign of the moment indicates the direction in which the force tends to rotate the rigid body. A positive moment implies counterclockwise rotation, while a negative moment implies clockwise rotation. Similar to the vector product, the moment of a force can be expressed in terms of its rectangular components. The formula for calculating the moment of a force with respect to a point using rectangular components is given by the determinant of the following parameters, where mx, my, and mz are the components of the moment on the xy, z axis, respectively. Fx, Fy, and Fz are the components of the force on the xy, z axis. Rx, Ry, and Rz are the coordinates of the point of application of the force with respect to the reference point. This decomposition allows us to analyze the moment of a force using individual components, which can be useful for certain types of problems. Varignon's theorem states that the resultant moment of a force system with respect to a point O is equal to the moment of the resultant force with respect to the same point. Although it may sound somewhat complicated, we can express it with the following equation. On the first side of the equation, the resultant force is first calculated and then multiplied by the position vector. On the second term of the equation, the moments of each of the forces are calculated separately, and these are then added vectorially. Both sides of the equation are identical in result. Varignon's theorem is a useful tool for simplifying the calculation of the moment of complex force systems. The scalar product, also known as the dot product, is a mathematical operation that applies to two vectors in three-dimensional space. The result of the scalar product is a scalar number, that is, a quantity without direction or sense. It is represented with the dot symbol and is calculated using the following formula, where A and B are the two vectors. A and B between bars are the magnitudes or modules of vectors, A and B, respectively. Theta is the angle between vectors A and B. With rectangular components, it can also be calculated as shown on the screen. The scalar product has the commutative property. This is that P times Q is equal to Q times P. It doesn't make much physical sense in this case to talk about the associative property, but the scalar product also fulfills the distributive property, as can be seen. The scalar product has various applications in physics and engineering, such as the projection of a vector onto another, or onto an axis, and the determination of the angle between two vectors. The moment of a force with respect to a given axis is a measure of the force's ability to rotate a rigid body around that axis. It is defined as the projection of the moment of the force on the axis, and this is achieved with the help of the scalar product. The formula to calculate the moment of a force with respect to an axis is equal to the scalar product between the unit vector of the axis and the moment of the force with respect to a point on that axis. Therefore, the moment of a force with respect to an axis is a number and not a vector. In the formula, MOL is the moment of the force with respect to the axis. MO is the moment of the force with respect to a point or any located on the same axis. F is the applied force. R is the position vector of the force with respect to a point or the axis. Lambda is a unit vector in the direction of the axis. You can also use the following formula for the calculation of the moment of a force on an axis, where lambda x, lambda y, and lambda z are the components of the unit vector in the direction of the axis. A torque is a system of two parallel forces of equal magnitude, but in opposite directions, that act along different and parallel lines of action. The effect of a torque is only rotational, that is, it does not produce a resultant force that can move the rigid body, but it will produce a moment that will tend to rotate the body. If we calculate the moments of the two forces with respect to a point, we get the following expression. It turns out that R(A) minus R(B) is equal to the vector R, which is the one that joins the points of application of the forces. This is very important and allows us to extract that the moment of a torque does not depend on the point with respect to which it is calculated. That is, it will always be constant. The vector of a torque is called a free vector. It can be applied at any point and will always be perpendicular to the plane where the pair of forces is located. The modulus of the moment of the torque can be calculated with any of the following formulas, where theta is the angle of the vector r with the vector f. D is equal to the distance between forces. The moment of a torque is measured in the same units as any generic moment, and these are Newton meter. A daily example of torques is observed when using a screwdriver. When tightening a screw, we apply a torque on the handle of the screwdriver that produces a moment that makes the screw turn. Two torques are considered equivalent if they produce the same moment and the same line of action. In other words, two equivalent torques can be exchanged without affecting the rotational effect on the rigid body. The equivalence of torques is an important property that allows us to simplify the analysis of force and moment systems through these same torques. In the image, we can observe three force systems acting on a rigid body. Although the individual forces and their distribution are different in each case, the three systems are equivalent. This means that they produce the same rotational effect on the rigid body, which is verified because the moment generated in each case is the same. This point is key for any good engineer, and it is that any force that acts on a rigid body can be decomposed into a force that passes through a point O and a moment with respect to O. In the following image, we can see that there is a force applied on a rigid body. If at point O, we apply two forces of equal direction and opposite sense, we do not change the state of this body. But if we look closely, we can see that we have generated a torque of forces that apply a moment at O. The force systems of each of the three images will produce the same effect on the rigid solid. The force at O has the same magnitude, direction, and sense as the original force, but acts at a different point. The torque has a moment equal to the product of the magnitude of the force by the distance between the line of action of the force and point O. A system of forces acting on a rigid body can be reduced to a single force and a torque with respect to a point O. Based on the previous point, we can reduce the three forces that are applied at different points of the rigid solid in the image to a single force and a moment at point O. The resulting force is the vector sum of all the forces in the system. The moment of the resulting torque is equal to the sum of the moments of each force with respect to point O. The reduction of a system of forces to a force and a torque is a fundamental technique for simplifying the analysis of complex force systems. Two different force systems are considered equivalent if they produce the same effect on a resting rigid body. For this to be fulfilled, the sums of the forces and the sums of the moments of these forces with respect to a given point O for both systems must be the same. According to the following formulas, the resultant of the force of the first system must be equal to the resultant of the second, and the same happens with the moments of these forces in O. And that's it for today's video. I hope you enjoyed it. Don't forget to subscribe to the channel to stay up to date with the latest news, and if you have questions or comments, don't hesitate to leave them below. See you in the next video. See you soon.